welcome speaker Bruce Allen, director of the Albert Einstein Institute in Hanover, and also professor at the University of Wisconsin, Milwaukee. Bruce did his PhD in, let me see, that was in 1984 with Stephen Hawking, and then after a couple of postdocs ended up in the University of Wisconsin, Milwaukee in 1989 as an assistant professor, and then stayed there as a professor until then becoming the director at the Department of Observational Relativity and Cosmology at the Max Planck Institute for Gravity and Gravitational Physics, the Albert Einstein Institute, where he is also present. So he's the leader of the Einstein at Home project for the LIGO scientific collaboration. He's working a lot with the LIGO collaboration. I think you're also going to talk about LIGO. And he's been working a lot on inflationary cosmology and also on cosmic strings. So it's we're very happy to have you here. We're looking very much forward to the talk, and so let's welcome him to Heidelberg.
Can you hear me okay? It's a pleasure to be here. This is my second trip to Heidelberg. My subject is gravitational waves. About 1,500 people around the world are working on trying to directly detect gravitational waves. And what you see here is a numerical simulation showing gravitational waves emitted when two small black holes collide and form a large black hole. This is the sort of process that by the end of the decade we hope to observe directly. Let me say also that if you want to ask a question during my lecture, please go ahead. Just shout or put your hand up. So I'm going to quickly talk about the fundamental physics, what are gravitational waves. I'll tell you something about how modern detectors work. And I'm going to talk about the sources of gravitational waves and what we might learn by the observation. The second generation of modern gravitational wave detectors is just now coming into operation. I'll tell you about the status of that and our expectations for the rest of this decade. And finally, because this is an astronomy audience, I'll also tell you about some of the possibilities for observing electromagnetically the counterparts of the gravitational wave sources. Finally, I'll say a little bit about the longer-term future. So, what are gravitational waves? How are they produced? Well, gravitational waves are really a consequence of the work that Einstein did in 2005 on the special theory of relativity. As you know, nothing can travel faster than the speed of light, and that includes gravitational forces. So, for example, the Earth is not actually orbiting around the place where, let's say, the sun would be in the sky right now. It takes light 8 minutes to reach us from the sun. And so, in fact, the Earth is orbiting around where you see the sun in the sky, not where the sun actually is right now, which is where you'll see it 8 minutes from now, as an example. So, gravitational interactions travel also at the speed of light. And this is actually what gives rise to gravitational waves. So the modern description of gravity, which came about, was discovered almost exactly 100 years ago in 1915, is the general theory of relativity. In general relativity, mass or energy curves the geometry of space-time, as you see here. So for example, light from a distant star is bent, and the star appears to be at a different location in the sky than where it actually is. The direct observation of that effect by Eddington in 1919 was the first direct proof or support for general relativity. gravitational waves are produced when massive objects are accelerated. And what happens is they emit gravitational waves away from the source. These are curvature in space-time which propagates away from the source. And you can see here at the bottom a numerical simulation that just shows what happens when two masses orbit each other. You produce these curvature ripples that travel away at the speed of light. Unfortunately, in the luminosity formula for gravitational waves, which have the square of the third time derivative of the quadrupole moment, there's a very small factor, Newton's constant divided by the fifth power of the speed of light, which makes gravitational waves very weak. Einstein himself thought they were too weak to detect, but we have better technology now. And just for completeness, the first prediction of gravitational waves actually was in this article in June 1916. So Einstein published the general theory of relativity in November 1915, and this was less than a year later. This article actually has a number of technical mistakes, and Einstein subsequently published corrections to it. He liked to publish. So until 1974, gravitational waves were only a theoretical prediction. But then, Joe Taylor and Russell Hulse discovered a pulsar called PSR 1913 plus 16. This system is a double neutron star. It consists of two neutron stars orbiting each other in a very elliptical orbit. And today, this elliptical orbit between the two stars has a size which is about 2 gigameters, so somewhat larger than the diameter of the sun. These two stars orbit each other about once every 8 hours. And what Hulse and Taylor discovered was an interesting thing. They found that the size of this orbit wasn't fixed. With each orbit, the orbit got 3 millimeters smaller. And by the way, the precision of that is always astonishing to me. How can you detect a 3 millimeter change in the orbit? You know, the orbit is 1 million kilometers in size. And you can detect that such a small change because these pulsars are extremely precise clocks. And that lets you map out the orbit. So what was happening? The orbit was decaying. And the reason it's decaying is because this system is emitting gravitational waves. And the orbital period, as I said, is about 8 hours. That means the orbital frequency is about 36 microhertz. This system is emitting gravitational waves at twice that frequency, at 72 microhertz, and is losing energy. Now, I told you it's 3 millimeters per orbit. It does about 3 orbits a day. So each day, the two stars come a centimeter closer together. And that means in a year, they come about 3 meters closer together. So in 1,000 years, they come 3 kilometers closer together. And in 1 million years, they come 300,000 kilometers closer together. In about 300 million years, this system is actually going to coalesce. These two stars will have lost so much energy to gravitational waves that they actually come together. And that's what we're hoping to observe with our gravitational wave detectors later this decade. So this system is a direct proof of the existence of gravitational waves. It's losing energy in a way that Newton could not have predicted. According to Newton's laws of physics, this system should just keep orbiting always with the same period. And it's not doing that. I have a plot here, but I think simply in the interest of time, I'm not going to go through this. Just to say that there's a plot here that shows over 25 years the way that the prediction of general relativity matches the data for how that orbit is changing. And a picture of Hulse and Taylor celebrating the Nobel Prize that they received in 1993 for this discovery. Okay, so I've told you what gravitational waves are. I've shown you that there's some direct evidence that they exist. We don't see the gravitational waves, but we see their effect. We see the energy loss. And so how can we detect these? Well, let me start by showing you some photographs of the current generation of gravitational wave detectors. This is one of the laser interferometer gravitational observatories. LIGO is the acronym. This one is in Hanford in Washington State in the northwest of the United States. This is located far from people, far from the oceans. And what you see, those two arms are actually concrete covers over long vacuum tubes. This is the LIGO detector in Livingston, Louisiana. These arms are 4 kilometers long. These two detectors are separated from each other by 3,000 kilometers. So about 10 milliseconds of light travel time. This is an analogous detector called Verdo. This is a French-Italian project. It's located in Cascin in Italy, not far from Pisa. And finally, this is the geodetector. This is operated by our institute. It's located about 15 kilometers away in Huta near Hanover. This is smaller than the other detectors and less sensitive. It's primarily used as a prototyping and development instrument, but many components developed here are actually in use in the larger detectors. There are also other gravitational wave observatories under development. This is called Kagra. This is a large-scale detector being built in Japan. It's actually located under a mountain. And the reason why is because if there's a seismic wave in the Earth's crust, it actually travels near the surface. So if you put the detector under a mountain, the wave actually travels over the mountain and doesn't go into it. So it leaves the detector undisturbed. It's a quiet location. And this is an interesting detector, which I think I won't go much into the details of. But these two 3-kilometer long tunnels have been built, and the detector is currently in construction. Okay, so these are pictures of the instruments. How do they actually work? So, to explain how they work, let me show you a thought experiment. Imagine that you're far in space, far away from anything. You're floating in space. So you're not near any disturbing masses, planets, the sun, anything. And you take some small masses, let's say little glass marbles, and you lay them in a ring, like that. So this ring is just floating in space, and you're floating next to it. It's a perfect circle. Now suppose a gravitational wave comes from behind the screen, traveling to you. This is what will happen to the marbles. Now this is exaggerated, but it gives you the idea. The marbles will start to oscillate like this. And this is a quadrupole pattern, because gravitational waves are a quadrupole form of radiation. And the period of this, the time it takes to go one full cycle, is the period of the gravitational wave. So gravitational waves affect the geodesics, the shortest paths in space-time, and the consequence is that objects move like that. But this motion, as I've written here at the bottom, is greatly exaggerated. So gravitational wave detectors use technology that wasn't available in Einstein's time. Ultra-stable lasers, modern electronic control systems. And the way they work, though, is based on that circle of masses. So now imagine that you rotate that circle of masses so that it's in the horizontal plane. And you get the idea. So these instruments consist of mirrors. There's 4 of them here. They're called test masses, which form an interferometer. So light comes in from a laser, it goes into a beam splitter, it goes into these 2 arm cavities, comes back out, and is recombined. You get fringes at the photodetector. Can one of the students here tell me what experiment this looks like? Somebody? You hopefully all studied this in your basic physics. Any ideas? It looks like a Michelson interferometer, thank you. The only difference is the Michelson interferometer has the mirrors fixed. They don't swing back and forth. These mirrors are hanging, and that means that they're in free fall in the horizontal plane for frequencies below the pendulum frequency. Sorry, for frequencies above the pendulum frequency. So above the pendulum frequency, these masses can move freely. So if a gravitational wave comes from overhead, like that, it causes one pair of mirrors in one arm to swing together, while the other pair of mirrors in the other arm moves apart. And then that reverses. And that causes a shift of the fringes back and forth. So this is how you detect gravitational waves. You monitor the distance between these two arms of what looks like a Michelson interferometer, and you look for the pattern where one arm gets bigger while the other arm gets shorter. This is what the instruments actually look like in real life. If you go into the central building, there are these large vacuum tanks. These actually contain the suspended optics. This is a laser bench. This is one of the mirrors. These are works of art. They weigh tens of kilos. And the surface of the mirror is precise to a nanometer, which is, a few atoms. So they're really very, very fine piece of optics. And this is part of a suspension system inside one of the vacuum tanks, just to give you a glimpse of what these look like. So, just to put the two pictures together, now I've rotated it so that the ring of marbles is in the plane of the screen. If a gravitational wave comes that way, it causes the pattern of the marbles to be distorted, as I showed you, and here is a kind of cartoon just showing the way that the distance between the mirrors also gets distorted. Okay, but how large is that change in length? It's really, really small. For the LIGO instruments, the length of the arms is 4 kilometers, and the change in the arm length that we expect from gravitational waves of astrophysical origin is about 10 to the minus 16 centimeters. Think about that. The size of an atom is 10 to the minus 8 centimeters. The size of an atomic nucleus is 10 to the minus 13 centimeters. We're trying to look for mirror motions that are 1,000th of an atomic nucleus in size. When you think about this, you're going to say, this is crazy, because look, the surface of the mirror is made of atoms, big bumpy things. But the light averages over the entire surface of the mirror, and the surface of the mirror has 10 to the 24 atoms in it. So the square root of that is 10 to the 12, so you can actually resolve the average position of the mirror surface much more precisely than the size of one atom, because you're averaging over many of them. So this is not an easy thing to do. There's a dimensionless number here, the fractional change in the length, divided by the total length, delta L over L. This is called the strain. It's about 10 to the minus 21, and that's the thing that characterizes the amplitude of the gravitational waves. If you go 10 times closer to the source, the strain will be 10 times bigger. If you go 10 times farther away, then the strain will be 10 times smaller. Okay, well, these instruments are a technological challenge to build. And the reason why is because, as you can imagine, these suspended mirrors are very sensitive. If a car drives by and goes over a bump nearby, it shakes the ground, and that shakes the instrument, and that shakes the mirrors. If there's too much gas in the vacuum system, the gas banging against the mirrors shakes them. If the suspension wires are hot, then they undergo thermal motion, and that shakes the mirrors. So this is a plot showing frequency on the horizontal axis from 1 hertz to 10 kilohertz, and on the vertical axis is the sensitivity, the strain sensitivity in strain per root hertz, this quantity delta L over L. And I've shown you different sources of noise. For example, the seismic noise here, this wall, is due to things like the waves hitting the coastline. They shake the ground. And even hundreds of kilometers away, that shaking of the ground translates into noise in the instrument. The shot noise here at high frequencies is due to the fact that to detect high frequency motion of the mirrors, you only have a short observation time. For example, to detect a 1 kilohertz gravitational wave, you have 1 millisecond in which you need to monitor the location of the mirror. In that 1 millisecond, only a finite number of photons arrive from the laser. And so there's shot noise, counting noise associated with that. At higher and higher frequencies, you have less and less time to make the observation. There's fewer photons, more uncertainty. So that gives rise to rising noise at higher frequencies. And there's other sources of noise, thermal noise in the suspension, and so on. Anyway, the sensitive region of the detector is roughly around 100 hertz. This is an audio band detector. If you could hear the gravitational waves, instead of measuring the motions of the mirrors, you'd be able to hear them. It's that frequency.
Sorry.
Please.
These figures have to refer to some special design.
These are referring specifically to the LIGO design, to the LIGO instruments.
The LIGO.
Yes. So LIGO is currently the most sensitive, the best of the instruments. It's the one whose data is the most interesting, and that's the one I'm talking about in general. All of the instruments, though, are based on the same technology and have similar curves, just with somewhat different numbers. So these different sources of noise mean that we're always working in the low signal-to-noise regime. Our signals are never strong. They're always hidden in the noise. And in fact, my part in this whole big project is the data analysis. I'm one of the people who does analysis of the data. And that means, roughly speaking, we take the output of this detector, we feed it into a large cluster of computers. This is our computer cluster in Hanover. And we search that data stream, cartoon is shown here, for weak signals, that's the blue, that's the red, hidden in the detector noise, that's the blue. And we don't know the parameters of the astrophysical signals. For example, we don't know the masses of the stars. And so that means that we can't just search for a single hidden signal waveform. We have to search for many different ones with different values of these parameters. So that makes it a large computing problem. Okay. I've explained something about how gravitational wave detectors work. Now let me talk to you a little bit about the science. So we have really one main motivation, and that is that right now we can study the universe with radio telescopes, X-ray telescopes, optical telescopes, but all of these things have a common feature, which is that they're telling us electromagnetic information. They're telling us about light, or radio waves emitted from the system. And there's things that don't emit any light or electromagnetic waves. For example, when two black holes collide and coalesce, they're black holes. Black. Light doesn't come out of them. So you can't observe that or detect that with electromagnetic instruments. You can, however, observe that process with gravitational waves, because these objects produce ripples in the curvature of space-time, and those travel away and give you some information. So one of our motivations is simply to have another way of looking at astronomical systems and to see things that we just can't see. The other motivation, I'll just quote one of my heroes, Richard Feynman, who said, "It doesn't matter how beautiful your theory is, it doesn't matter how smart you are, if it doesn't agree with experiment, it's wrong." So we'd like to test general relativity. Now, I'm a card-carrying member of the General Relativity Society. I really believe general relativity is right. So for me, frankly, this isn't much of a motivation. But it is a reason to do it. Okay. I explained to you that one of the sources we're looking for is the gravitational waves emitted when two neutron stars like the Hulse-Taylor binary pulsar system, coalesce. So these are systems that form. We know of about 10 such systems in our galaxy now. And these systems, the stars, orbit each other for millions of years, gradually, slowly emitting gravitational waves. But then at the end of their life, in a brief burst that lasts just a fraction of a second, these stars orbit around each other hundreds of times per second, very briefly emitting a huge amount of energy as gravitational waves. And then they coalesce together and form a black hole. And so, in our entire universe, in the 14 gigaparsec diameter of our visible universe, this process of two neutron stars merging together happens every 5 minutes. Unfortunately, our detectors don't see the entire universe. They're not so sensitive. We can't see so far. So, in the initial version of these instruments, we could see about this process in a distance of about 20 megaparsecs. Roughly speaking, would happen once every 100 years. In the next generation of instruments, which I'm talking about in this talk, we expect to see this tens of times per year. I said these gravitational wave signals are in the audio band. If we could, if they were sound and not gravitational waves, we could hear them. And just for fun, I've got here a little recording showing what you would hear. I'll just play that one more time. That's a chirp. You notice the frequency is increasing. That's because as the stars orbit each other and lose energy, they go faster and faster. That's why the frequency is going up. And it also gets louder. The amplitude goes up because the gravitational wave emission gets stronger. Similar signals would also be produced by a neutron star orbiting a black hole or two black holes orbiting each other. The waveform of such systems has three parts. There's a part when the two stars are orbiting each other slowly enough that the curvature of space-time is relatively small, and we can calculate that part analytically. Then there's a part when the two stars are merging together. That's when the gravitational field is strong in absolute terms. The nonlinear properties of general relativity mean you can't do this analytically, only on a supercomputer. And finally, there's a last phase when the black hole that formed settles down to the Kerr solution, to a rotating black hole, and the last perturbations get radiated away, and this part can also be calculated analytically. This provides us with a stringent test of strong field gravity, because we can compute these things either analytically in our computers and compare them to our data. Seeing how often this happens provides a very nice calibration for stellar population synthesis. As you tune the different parameters in stellar population models, you come out with different numbers, for example, of black hole or neutron star binaries. So actually making these observations and seeing how often this happens will tell us a lot about how stellar populations evolve. And finally, as I'll explain at the end, this is also a likely source of electromagnetic signals, at least for the neutron star case. Another potential source of gravitational waves is simply from rapidly spinning neutron stars. These stars are about 50% more massive than our sun, but they're compressed into a radius of about 10 kilometers. And if these stars have even a small bump on them, a little mountain, just a few centimeters high, as they spin, that mountain will emit gravitational waves. There's other mechanisms as well. For example, if the neutron star is accreting mass from a nearby companion star, that can also create something like a mountain where this matter comes tumbling down. That's another source of gravitational waves. We've actually searched with the data from the existing instruments for gravitational waves from all of the known pulsars, radio pulsars. which are spinning at the right rate and not seen anything. We've actually obtained some very good upper limits. For example,
what does that mean? That means you filter at that frequency?
Almost. You filter at twice that frequency. If the star is spinning at 100 times a second, the gravitational waves are 200 times a second. But that's precisely what we mean. And these stars, they're tracked by radio observatories. They spin at such regular clocks that you typically make some observations, and you come back a couple months later and make some more. And you can say the star has rotated, 106,421,375 times since the last time I looked at it, and just keep tracking that rotational phase. And so that's precisely what we do. We look for gravitational waves at twice that frequency. And the best limits we've gotten, for example, on one star show that if it has a bump like this, that bump is less than 10 to the minus 7 times the radius of height. Quite an amazing number. This star is 10 kilometers in diameter, 10 to the 6 centimeters in diameter. If it has a mountain on it, that mountain is less than 1 millimeter high. Otherwise, it would produce gravitational waves that we would have observed. Searching for systems like this, so we think that our galaxy has about 100 million neutron stars in it. Radio astronomers have found about a bit more than 2,000 of them as radio pulsars. So there's still 100 million out there. Probably the closest neutron star to us is only 10 or 20 parsecs away from us. And so one of the things that we've been doing with our gravitational wave data is searching for neutron stars at unknown places in the sky and at unknown frequencies. This is called the all-sky, so we're looking over the whole sky, blind search problem. It's blind because we don't know what the frequency is, we don't know how the frequency is changing with time. And that is actually a very large computing problem, and we use Einstein at home exactly for that. You mentioned that in your introduction. It's a bit of a long shot. I'm actually not that optimistic that we'll see gravitational waves from spinning neutron stars with our next generation of instruments, but if we do, we should be able to learn a lot about what's going on inside the stars, especially if the neutron star has a glitch. Sometimes neutron stars don't spin regularly. There's some kind of a starquake on the surface, or the magnetic fields rearrange themselves inside the star. Something happens which causes the spinning to become a bit irregular. And so if we can observe the gravitational waves and the electromagnetic spinning, or something else about the star, we can learn about what's going on inside. Okay, another possible source of gravitational waves is just, let's call them bursts. Roughly speaking, the last 1 or 2 seconds when 2 neutron stars or black holes merge makes a burst of radiation. But there's other sources. For example, when a neutron star, if it's secreting matter, it eventually goes over some limit and collapses to form a black hole. That might produce a distinct burst of gravitational waves. Or if a normal star undergoes core collapse to form a supernova, assuming it's asymmetric, not too symmetric, that should emit gravitational waves. There's other potential sources as well, exotic things like the cusps on cosmic strings. So this is another type of source that we look for. And finally, there could also be a stochastic background of gravitational waves, somewhat analogous to the electromagnetic radiation discovered by Penzias and Wilson in 1965, and most recently observed with the Planck and WMAP satellites. There are things called pulsar timing arrays that are looking for the low frequency version of this. I think because of lack of time, I'm not going to talk about it now, but you can ask me about it in the discussion. And there were reports almost a year ago from the BISEC 2 experiment that had seen very low frequency gravitational waves. It's now thought that this is actually not gravitational waves, but instead emission due to polarized dust in our galaxy. Good. So the LIGO scientific collaboration has been analyzing data from our first generation of instruments. We've published 91 papers. So far, we haven't detected any gravitational waves, but we are optimistic for the next generation. I would like to comment that the improved data analysis methods have actually been very useful for radio and gamma ray astronomy. In my group, we've discovered many new radio and gamma ray pulsars using the same technology in recent years. I was also very happy I discovered that one of the data analysis techniques I invented 10 years ago for the gravitational wave search actually is an integral part of the Kepler satellite data analysis pipeline. It eliminates almost all of the false positives. So these techniques are useful, but they haven't actually succeeded yet with gravitational waves. Okay. So let me talk now about the remainder of this decade, the next, say, 5 years. I'm very optimistic about what's coming. So in the United States and Europe, the next generation of these instruments is approaching completion. The LIGO instruments finished their 1 year of observation in 2009, and before that, in 2008, the United States National Science Foundation began funding an upgrade to improve the sensitivity by a factor of 10. Now, you think a factor of 10, so what? But a factor of 10 lets you see 10 times as far. And if you can see 10 times as far, the volume that you can see is 1,000 times more. And you remember I said that our event rate in the initial instruments for binary inspiral was about 1 every 100 years. You multiply that by a factor of 1,000, which is what the order of magnitude increase in sensitivity does, and now you get 10 events per year. So in 2010, the initial instruments were dismantled, and the construction actually finished late last year, and we're now in the commissioning mode. And I'm very happy to report that in December 2014, the LIGO instrument in Livingston had a 1-week test run where it achieved an inspiral range of about 60 megaparsecs. So it's already a factor of 3 better than our first generation instruments. And there's one more remaining factor of 3 to go before it gets to its design sensitivity. We're going to do our first science run this spring or summer. We hope to have a sensitivity of about 80 megaparsecs at that time. And by the way, this shows one of the suspensions for the advanced LIGO instrument. These are the pendula containing the mirrors. It's in 2 stages. This is basically an isolation system that's designed to isolate the shaking of the ground from the mirrors. Okay. As I explained earlier, we don't know how many double neutron star binaries there are in the universe. This is our benchmark source. But a careful study indicates that we can expect about 1 event per week. And let me just show you the reference for that briefly. This is a paper published by our collaboration in 2010. It shows the detection rates in the instrument for compact binary coalescence sources. The upper part of the table is for the initial generation of instruments, the ones that were decommissioned in 2010. And the lower part here shows the advanced generation, the ones that are now coming on into operation. And for example, the advanced instruments here, this is the neutron star binaries, neutron star black hole, and double black hole systems. And for each of these systems, we have actually 4 different rates. We have the lowest rate that's consistent with what's observed in the population of stars in our galaxy, a realistic rate based on our best understanding of what the observational and systematic biases are, a high limit, this is if nature is particularly kind to us, and this is a maximum that we think is consistent with what we know about stellar populations. And the realistic number here is that we expect, when our instruments reach design sensitivity, about 40 neutron star inspiral events per year. So roughly 1 per week. In the most pessimistic case, and you can ask me about what the pessimistic case is in the discussion, we'll have to wait about 2 years before we see a signal. I think that's unlikely. So this next generation of instruments should really allow the direct detection of gravitational waves. Okay, well, I have a little bit of time left, and let me just talk briefly about some of the other things that one could do to look at electromagnetic sources together with gravitational waves. And I need to explain something first, which is that these instruments are not like telescopes in the following way. You know, Chandra, you point at the sky and you can see with half arc-second resolution a patch of the sky that's half a degree in size. Similarly, Fermi or the Arecibo telescope, they point at a particular part in the sky. Our gravitational wave instruments don't do that. They are sensitive to signals coming over through the entire sky. It's like an antenna. It's not a dipole antenna, it's a quadrupole antenna. And so this peanut here shows the antenna response function. We have the most sensitivity, that's +1 for signals coming from directly overhead, over the plane of the detector, and sensitivity -1 for signals coming from directly underneath. And we have 0 sensitivity along a line that's 45 degrees between the two arms. But basically, we can detect signals from the entire sky at once. This instrument doesn't point. So if you want to know where a signal is coming from on the sky, you have to use multiple instruments. You have to use the time delays between instruments. And as an example, if there's a signal coming from this point in the sky, it will arrive first at the European detectors, and then some milliseconds later at the ones in Japan and the one that's being built in India, and then perhaps 20 milliseconds later at the LIGO instruments in the United States. And so by using those time delays, you can figure out roughly where the source is on the sky. And all the instruments have a data sharing agreement so that we can implement this in practice. How precisely we can determine the arrival time, it's not based on how precise the clocks are. We have nanosecond precision clocks at the sites. It's based on how precisely you can locate the waveform. Because you're comparing a waveform that's oscillating at one instrument with the waveform that's oscillating, then you have to line them up. And these are audio frequencies, so probably you can line them up to a millisecond or a fraction of a millisecond. And that means that your pointing accuracy is at most a few degrees. And the point spread function, your uncertainty, is not a nice ellipse or circle on the sky. It's a sort of messy blob of probability regions. So this is, for example, the probability region associated with the sky for a particular simulated event. You know, it's most likely the highest probability that it's there, but then there's also some other islands of probability nearby the sky. And the reason you get these separated islands is if you slide your waveform by one complete cycle, it's still a good match. And that shifts you over in the sky. So each island corresponds to shifting the waveform another cycle. And unfortunately, during the next few years, we expect that this uncertainty region is going to be hundreds of square degrees. So this makes it rather difficult to locate optical counterparts or other counterparts. By the next decade, by the 2020s, there will be more instruments in operation, and one can do this triangulation better. So what are our expected first detections? Well, we have a schedule for how the instrument's sensitivity is going to change over time. As I said, we're going to do our first science run in 2015, which is going to last for 3 months. We expect to have a binary inspiral range between 40 and 80 megaparsecs. And depending upon the rate of binary inspiral, we'll see anywhere between 0 and possibly as many as 3 signals. You can see that the instrument sensitivity will increase over the coming 2 to 3 years. And I think by the time that we reach ranges of 100 to 200 megaparsecs, we're going to be making our first detections. So this is really coming rather soon. How am I doing for time? Another 5 minutes? Come on. That's the first time I've destroyed a lecture hall. Sorry. Yes. Thank you, I'm sorry. Okay. 5 more minutes? Okay. Just so let me know when this is when I should wrap up. So I just wanted to say a little bit about doing transient astronomy together with gravitational waves, because I know that there's people here in the audience who know a lot more astronomy than I do, and I thought this would be interesting to you. People thought for a long time that the sky was a very static place. And in fact, it was radio astronomy that changed that. The development of radio telescopes indicated that there was a lot of dynamic activity in the sky. Processes which were taking place on short time scales, which weren't previously understood. And the latest generation of optical instruments is designed in part to capture these transient short-lived phenomena. For example, there's something called the Large Synoptic Survey Telescope. And synoptic has something to do with changing in time. This is going to come online in 2020. There's a roughly 1 meter class instrument called the Palomar Transient Factory. It's a robotic telescope and data analysis system which is looking for changing things in the sky. It's found a lot of new classes of supernova, for example. And there's telescopes like the Swift satellite, which is looking for gamma ray bursts, which are another transient thing. And these might, in some cases, be accompanied by gravitational wave emission. So, for example, long and short gamma ray bursts, magnetar flares, radio pulsar glitches, or some neutrino events. These may all be things where there's a accompanying production of gravitational waves. It's something to look for. And of course, if you know where your optical or other electromagnetic signal is on the sky, that immediately tells you what the time delay is to search your signals for. You also have a rather short time window to look for, since electromagnetic waves travel also at the speed of light. So this means you can do a more sensitive search. You can search only a little bit of your data, and you can search it, let's say, with only one time delay between the instruments instead of many. This would also be a wonderful thing for our gravitational wave science if we could simultaneously make such a detection, because we really have a lot of confidence that the gravitational waves were real and not just a car a few kilometers down the road driving over a big bump at one instrument at the same time as another car drove over a bump at the other instrument. So it would be good for our confidence. But the gravitational wave error boxes, as I explained, are hundreds of square degrees, and you don't have very long to capture the electromagnetic signals. The gamma rays flash probably be gone in seconds. The optical glows might last hours or days. This is also a political topic, which I think I'm again not going to go into now. You can ask about it if you want. It's believed that short gamma ray bursts are probably the result of neutron-star coalescence. By the way, it's also now believed that this forms many of the elements in the periodic table that are in the rare elements. So maybe the rare elements are actually a result of neutron-star coalescence. And there's been numerical work that shows that when you merge together two neutron stars, the magnetic field configuration that forms produces some kind of a jet-like structure. The rates also match. We don't know for gamma ray bursts how broad the beam is that comes out. There's a plot here that shows the potential opening angle of that beam from, say, 0 to 90 degrees. If the opening beam is very narrow, then it's hard to see these events. And the fact that we've observed, say, 900 of them in the last 10 years means that there must be a very high underlying rate. If the beam is very broad, then we see almost all of them. And the fact that there's 900 in the past 10 years means that the rate's not so high. So this is a plot in red showing the expected rate per cubic megaparsec of gamma ray bursts depending upon the opening angle. And you can see, just in the rate plots, that it's a rather good match for what we expect for the neutron-star, or for the binary, or for the neutron-star black hole scenarios, if the opening angles are somewhere in the range from, say, 10 to 30 degrees. which is also what's theoretically believed. So this is one potential source for simultaneous observation. There's one other plot here, which I've shown, which again has the gamma ray burst opening angle in degrees. And the vertical axis shows the expected number of coincident observations, gravitational wave plus gamma ray burst, per year, using our two different orbiting instruments, Fermi and Swift. And you can see that the numbers, for example, for Fermi, are somewhere in the range of order 1 per year. So our hope is that we'll observe tens of binary inspiral events per year with our gravitational wave detectors, and we might see once a year a coincident gamma ray burst. And lastly, it's also possible that there are going to be optical counterparts visible with optical telescopes. You see, when two neutron stars merge, it's a very violent process, and some of the matter gets ejected. It doesn't all end up in the black hole. And think about that matter. This is matter which is at nuclear density. It's 10 to the 15 grams per cubic centimeter. It's like you took an entire mountain and squished it into something the size of a sugar cube. So when some of this matter gets ejected from the stars and goes flying off into space, some dramatic things happen. There's nuclear reactions, our process reactions, that neutron-rich matter gets converted back into more ordinary matter and decreases in density. And it's believed that this may produce optical bursts that are called sometimes kilonova. They're expected to be about 1,000 times as bright as a classic nova. And in some recent work, the conclusion is that if you build 1 meter class telescopes with very wide field cameras, so you can look over this hundreds of square degrees in the matter of hours, there's a good chance of catching some of this transient optical radiation. And this is a plot, this is a table I've taken from this paper, just showing that, for example, for the next generation of the Palomar transient factor, which is called the Zwicky transient facility, which has about a 1 meter aperture, they expect that they should be able to detect somewhere between 6% and 94% of all gravitational wave sources in this way, but the actual number depends on the intrinsic magnitude of this optical burst, which isn't known. Okay, I think I'm wearing out my welcome. Let me just very quickly flash through 1 or 2 more slides and then conclude. I just want to say something about what might happen after the next generation of instruments. In Europe, we're gradually going through the planning of the next generation, the 3rd generation instrument called the Einstein Telescope. This would be something on the scale of CERN. It would be underground to reduce seismic noise with a triangular configuration, so not quite like a Michelson interferometer. This lets you detect both gravitational wave polarizations simultaneously. This is something on the scale of CERN, probably similar costs and lifetime. A system like this would be able to see another order of magnitude farther. So it could basically see all of the neutron-star coalescences in our Hubble sphere, invisible universe. So with rates that are another factor of 1,000 greater, so every few minutes. There are also ongoing plans to build a low-frequency gravitational wave detector called LISA. This is planned as the 3rd large ESA mission for launch in 2036. It consists of 3 spacecraft separated by about a gigameter, and will be sensitive to gravitational waves at much lower frequencies. For example, such as those produced by orbiting white dwarf binaries. Those stars never get close enough together to emit gravitational waves in the audio frequency, but they emit at lower frequencies. And a Pathfinder satellite is going to be launched later this year to test the key technologies of this. So this brings me to conclusions. We expect that by the end of this decade, the network of gravitational wave detectors will be making its first detections. The most likely sources are the coalescence of two neutron stars, or neutron star and black hole systems. Potentially, we may also observe electromagnetic signals, coincident with those from gamma ray or optical telescopes. From the gravitational waves alone, we won't be able to say exactly where in the sky these events took place. If we have an optical or gamma ray counterpart, then we'll be able to specify that. And somewhat in the longer term, if you look at the history of X-ray astronomy, the first extraterrestrial X-ray sources were discovered in the 1960s with balloon-based experiments. It took about 40 years from that to the launch of the Chandra Telescope, which is an exquisite instrument that has arc-second resolution on the sky, has revolutionized X-ray astronomy. And I expect that gravitational wave astronomy will have a similar future. After we make our first detections, I expect there's going to be a rapid evolution in the field, and within a few decades, this will be a high-precision standard operating tool for astronomical science. And I just conclude, if you want to help us with our searches, please consider installing Einstein at home on your computers. That helps us search for signals. Thank you very much. That's a good question. I'm not the right person to ask that question because I'm such a believer. It's like asking, a religious person, what if God doesn't exist? They won't even answer the question for you. If we don't observe something after running these instruments for 3 years at their design sensitivity, it really means something dramatic is wrong. Either our understanding of how stars evolved is badly wrong, or the theory of general relativity is badly wrong. I don't see how general relativity can be badly wrong because it's been tested, for example. We know gravitational waves exist because we see their effects. Not just in 1913 plus 16, but also in other double neutron star systems. So I don't think GR is wrong. What we know about double neutron star binaries comes from our own galaxy. We know of at least 10 double neutron star systems in our whole galaxy. We think there are many others that we don't see, because we think there's a distribution of luminosities, and we see the brightest ones. So if you extrapolate the luminosities, there are many dim ones that we can't see with radio telescopes. So our number of 40 per year, 40 gravitational wave events per year, is based on that extrapolation. If that extrapolation was wrong, if the only double neutron star systems in our galaxy are the ones that we actually see with radio telescopes now, then you get that rate of 0.4 per year. We wait 3 years. If we wait that long and we still don't see anything, it means that our galaxy is very untypical. That the fact that we have 10 double neutron star binaries in our galaxy, well, our galaxy isn't like most. Most other ones have far fewer. And that seems crazy to me. But, so that's the best I can do. I'm sorry, I don't have a good answer.
Other questions from students in both blocks?
Likely is it that you just overestimate the sensitivity?
We measure the sensitivity. So here's how you calibrate the instrument, okay? The first crude calibration we do is you swing the mirrors back and forth. And if you swing them by half a fringe, or maybe it's a quarter of a fringe or whatever, you see the interference fringe shift completely by one fringe. Okay, so you know how much motion corresponds to how much shift. Now the actual shifts that we observe are much smaller than that. But now, what we do is we actually push the mirror. And we push it first with a little coil. There's a magnet in the coil. You put current to the coil that generates a force and shifts it. And that's F equals ma. I mean, from the current and the magnetic field, you can calculate what the force is. From the mass and the force, you can calculate how far you moved it. So our calibration is good to, the biggest error is a few percent. It's just based on Newtonian mechanics. And that's an absolute calibration. So I think it's fair to say we know how our instruments work. Maybe not to 0.1%, but we certainly know how they work to 5 or 10%. So I rule out calibration errors.
The question of sensitivity, so what are those values?
Oh, well, all I can say is that we're actually ahead of schedule now. Our instruments are currently more sensitive, that is, the noise floor is lower than it was supposed to be at this point in development. And for the initial LIGO experiments, well, some of the experts tell me that it's purely coincidence that the instruments came out to be at the sensitivity they were designed for, but they did. This next generation of instruments is a lot more professionally designed. We have a lot more experience. I just think it's going to work. Could be wrong.
Do you have to worry about strange quantum effects if you have this high sensitivities with this?
It's a good question. Well, I guess shot noise isn't a strange quantum effect, right? Shot noise is a quantum effect. The particles of light are arriving one after the other and not necessarily evenly. I don't think we need to worry about it, but there are ways of exploiting it. There's some interesting things called quantum non-demolition. They're based on the idea that Heidelberg's uncertainty principle, delta x delta p is less than h bar over 2 to 4. That the uncertainty principle is a constraint on either position or momentum, but not both. And so what we want to measure in our experiments is actually the position of the mirrors. And so you can do things called squeezing light, which lets you measure the position more precisely because you lose some precision in the momentum measurement, which you don't care about. And so actually exploiting strange quantum effects, the squeezing of light, will actually allow us to build instruments which exceed the sensitivity which you would naively expect from sort of back of the envelope application of quantum mechanics.
Okay, so that's all for everybody. I saw a question over there. Yeah.
Just for the sensitivity again, what are the present obstacles with the new detectors to reach the full factor of 10 over the previous detector?
So when I was an undergraduate, I did experimental work and I built a lot of electronics. And when I started off, I'd have my electronics circuit that I designed, I'd build the whole thing and it wouldn't work. And then after experience, I got better at this. First I built the power supply and get that working. Then when that was working, I'd build the input stage and get that working. And then I'd build the next stage, I'd build it piece by piece. An instrument like this is a lot more complicated. And the same approach is the one that's followed. So the different subsystems are first built, the laser and characterized, and then the suspension systems, the feedback system, and so on. And then they're integrated together. And that integration is a commissioning process which goes step by step. So right now, the next stage is going to be increasing the amount of light going into the instrument. Right now, the lasers are turned down so that they're not producing a lot of light. But the next stage is going to be to increase the amount of light, which is going to push down the shot noise at high frequencies. And that introduces new instabilities in the control systems. For example, the extra light arriving on the mirrors heats the mirrors. That changes their shape. So now a compensation system, which heats the back of the mirrors to curve the back into the right shape, dynamically has to be commissioned and made working. So I don't actually know right now what the next stage is. I believe it's increasing the laser power. But each of these stages involves, changing something in the instrument and then trying to get everything working again and understand what new effects have arisen and how that can be compensated for.
So, I have a question. So we talked about measuring and putting these detectors underground. Can you compare a little bit the different strategies of making underground in space? For instance, you had a curve which was a seismic noise. How much does it change putting underground? because if you say it's comparable cost with CERN, it's much more expensive than putting in space, I think so, right?
Yep.
So can you comment on that?
Sure. So first of all, the space-based detectors will operate at a much lower frequency range. They'll be sensitive to signals that are, let's say, millihertz signals. So very slow oscillations. In absolute sensitivity, the strain, the fractional displacement divided by the total length, they're actually not as sensitive as the ground-based instruments because of this lower frequency operation. So unfortunately, you can't take the ground-based instrument and so easily put it in space. It's not on the small scale. It's hard to build something so sensitive and make it work in space. The large baseline instrument at lower frequencies, that will work well in space. You can't do that on the ground. To answer the other part of your question, I believe that the Kagra people, by the way, their experiment is actually not underground, it's actually under a mountain. So the mountain is actually above the ground, and the tunnel is actually in the mountain. It's actually above sea level. It's just underneath the mountain. I think they gain about a factor of 100 in low frequency, in moving this seismic noise down. Unfortunately, it has a very steep slope, and so that gains you some extra low frequency sensitivity. I'm afraid I don't know the number. I'm sorry.
What's the PSF of the Einstein Telescope?
What's the one?
What's the PSF of the Einstein Telescope?
The point spread function.
Yeah.
2 pi is the radians. It doesn't, remember that you only get your pointing from having multiple sites, right? I went through that. You need triangulation for the arrival times. And if you just build an Einstein Telescope in Europe, that's one site. It can sense both polarizations, but it has no pointing at all. It's an antenna. It sees the whole sky. So the United States would have to build such an instrument. India would have to build such an instrument. We need multiple sites like that around the world if you wanted to get a point spread function that was down to, let's say, some square degrees.
How will you convince the astronomy and physics community that your detections are real?
That's a very good question.
You showed that formally the signal to noise is very low.
Yeah.
You apply complicated algorithms to a time stream, and then you get out a detection which is formally significant, that requires that you have perfect understanding of the statistical distribution of your noise.
Yes. So, a very good question. A couple points here. Actually, the data analysis looks complicated, big computer clusters, what look like complicated neighbors. It's actually not. It's actually matched filtering. You take f1 of t, you multiply it by f2 of t, f1 is your template, f2 is your data, and you integrate dt. Okay? Of course, we do it in the frequency domain. We have a lot of different waveforms and stuff. We do plan to release the data sets for any detections, along with the software that was used for them. And the algorithms are actually not very complicated. So, first point is, the data analysis ain't so complicated in the end. That's point number one. Point number two, the waveforms that we're looking for the binary inspiral actually consist, the signals will last a few minutes in these instruments, let's say 5 minutes, and they're at 100 hertz. So they're doing 100 oscillations per second for 5 minutes. That's 300 seconds and 100 oscillations per second. It's like 30,000 oscillations. And we can predict analytically and with computer simulations how the frequency and the amplitude of those 30,000 cycles should change with time. You know, the frequency is going to increase, the amplitude is going to increase. So when we find something in our data, it's going to be something which matches that waveform. Now there are, it's true, we can't characterize the detector noise perfectly. It's not a Gaussian random process, for example, but we still have a pretty good handle on it. And we can do things, for example, like determine our false alarm rate by sliding the data at one instrument at a time. So for example, if we take our data set, but then we shift the signal in one instrument by 5 minutes, that's much greater than the light travel time between the instruments. So now we've wiped out any real signals. So we can do many such time shifts like that and use that to characterize the background. And so we do actually have, we can't characterize our noise statistically so well, but we can do experiments like that in Monte Carlo studies to characterize what the false alarm rate of our data analysis pipelines is. What can I say? In the end, we'll do our best to convince everybody that it's real, but it sure would be nice to get an optical and gamma ray burst at the same time. Then nobody would question it.
Any maybe crazy or very
there are. One of the ideas is to build, so gravitational waves, are just like any other wave. We expect the cosmological gravitational waves to have frequencies of 10 to the minus 16 or 10 to the minus 17 hertz. That is, they've done a few oscillations since the universe began. The ones we're looking for are audio frequency. The ones from the Taylor binary pulsar now are 30 or tens of microhertz. And there should be gravitational waves also at higher frequencies, right? With much shorter wavelengths. And so there are papers in the literature where people are proposing crazy ideas about how to detect gravitational waves with frequencies of megahertz or tens of megahertz. And the idea, roughly speaking, is you build a very precise microwave cavity that's tuned. And when a gravitational wave comes by, there's a Feynman diagram where a graviton interacts with photons and has the effect of changing the Q of this cavity slightly. So you see a dip or a boost in the resonant energy in the cavity. It's a crazy idea. Who knows? 100 years from now, I'm sure that will be a solved problem.
Regarding the black hole system, if you have spin configuration, you actually get an anisotropic emission of gravitational waves also the resulting black hole decay. So first question, how does this affect sort of compared to the neutron star or neutron star black hole systems you talked about? And second, has this effect been accounted for in your population study?
Two very good questions. First of all, in terms of the population studies, very little is known about black hole populations. And so some work has gone into trying to do the estimates of the black hole rates, what you saw on my table there. But the error bars are quite a bit wider, and I think that's on less solid ground than the other estimates. That's the second part of your question. The first part of your question, you've actually just described one of the very active areas of research in my research group right now is we're hard at work developing data analysis pipelines to search for systems where they're highly spinning. Because the black holes that have been studied carefully, where the spin can be measured, are almost all extreme. They're almost all spinning almost as fast as it is possible. And so that causes modulation of the waveforms. And depending upon how the spin axes align, it has a big effect. What that does is it means that instead of just being able to search, say, mass 1 and mass 2, a 2-parameter family of waveforms, so we've got a much bigger parameter space where the spins, their relative orientations, how that's aligned, all that matters. And so in fact, we're very hard at work right now trying to develop a data analysis pipeline that is sensitive to such systems. I think that's kind of a partial answer to your question.
But we have not accounted for this effect in the population study numbers there, so it could potentially boost this number or drop it.
I would say that has a big effect on the black hole systems. For the neutron star systems, the fastest spinning neutron star that's been found by radio astronomers is spinning at 700 and something, 730 hertz, I've forgotten now. If you calculate, we don't know exactly what the radius is, but if you calculate how close that is to extreme spin, it's still not spinning so fast. For the neutron star systems, probably the spin can be neglected. It's not going to have a big effect. For the black hole systems, it's probably going to matter a lot. So I think we'll be able to detect our neutron star systems okay. I'm not so sure that we're quite ready yet
detection, how would you determine the nature of the source, whether it was black hole, neutron star?
So, these systems are not going to be so far away. If they're neutron star systems, they're going to be at distances of 200 megaparsecs. So, redshifts, it's less than 0.1 or something like that. The black hole systems are similarly not going to be so far away. So just from the waveform, we can already compute what the masses are to reasonably good accuracy. So we'll know what M1 and M2 are. We'll have some idea where it is on the sky. If there's no electromagnetic counterpart, unfortunately, it's not going to be so precise. Repeat your question again. I'm sorry, I just lost my train of thought.
So when you detect it, is there a way to determine what the nature of the source is?
Yeah. So for example, if we see this kind of in-spiral chirp, the thing that I played over the the audio system for you, there'll be thousands of cycles of that waveform, and by matching, fitting to those thousands of cycles of waveform, we'll be able to tell you at least what the masses are, what the distance is. We'll be able to tell you how the orbital plane was inclined, maybe something about the spin, maybe. That's about it.
Okay, there was one final question.
Yeah, so how well do you know the Earth? So how well do you know it's not until now unknown signal? I mean, you can't predict an earthquake or something like that. And with this fine detectors, how can you be sure that it's not something which has not been known until now?
So do you mean how can you be sure, for example, this detector isn't just picking up, let's say, a kind of earthquake in the ground or something? Yeah, it's a good question. So in the instruments, these instruments take data and they collect data. And the data, for example, the gravitational wave channel, it's almost like an audio stream. You can listen to it if you want to. It's a few kilobits per second. That's one data stream. But coming out of the instrument is about another 1,000 data streams. And there are things like seismometers located near all the optical mirrors, and radio sensors that can sense electromagnetic interference, and accelerometers that measure motion, and dust sensors which measure dust levels, and on and on and on and on. So everything that can possibly have some effect on this instrument, sort of through the environment, is monitored. And actually the monitoring is very useful. At one point we thought we had a signal of something that would look interesting. It turned out it was an airplane flying overhead. And it was acoustically coupling. There's other examples where you can listen to people talking, for example, in the control room on some of our channels, because it sort of leaks in. So there's a lot of stuff that gets monitored. So the short answer to your question is, first, if we think we've made a detection, we're going to look very carefully at everything around the instrument that is going on. But secondly, we should see this in two instruments. We should see the same signal in two instruments that are thousands of kilometers apart from each other, with a time delay that's milliseconds. And it's hard to produce that kind of coincidence through, let's say, normal human activities. Anyway, it's not a very satisfying answer to your question, but we try to be careful.
Okay, so I would say let's